OK, there we go. So howdy, everybody. I'm Pete. I've been coming to this group on and off since 1990-something. I don't actually remember when. So some of you may have seen me around before. So a little bit about what's behind tonight's talk. So some of you know Walter. And one day, Walter was suggesting, hey, Pete, why don't you come to the D conference and give a talk? Well, maybe I should learn D first, since I haven't actually learned it yet. He said, you know what? Not every talk needs to be right at the cutting edge. There's room for lots of intermediate and beginner level talks, which got me thinking, you know, with C++, there's some things that I learned a long time ago and have then forgotten and have had to relearn. Maybe that'd make a good topic for our talk tonight. So if you have any questions, go ahead and ask them during the talk. As soon as I get to the end of the slide, I'll stop and check for questions. Or you can ask me more questions afterwards. Either one will work just fine. And let's get started. So a long time ago, Scott Myers came here, and Herb Sutter was also at Microsoft. And I went to listen to them talk about the new upcoming C++ 0x, which meant that they hoped that C++ 11 would be done in a year that started with the 0. Well, they were off by a little ways. But a couple of the features they talked about was copy elision, which is using move constructors instead of being able to copy things. And I thought, wow, that's cool. But then when I went back to work, I was working at Microsoft at the time, I couldn't use it. We couldn't even use STL. We were working in the Windows networking team. And we just weren't allowed to use those newfangled features yet. And then I moved on to the Windows Live Messenger team, and they weren't allowed to use those newfangled features. We couldn't even use ATL. And then I went to Amazon, and they weren't using the newfangled features yet. And then I went to Google. And finally, last year, the Chrome team started allowing use of the C++ 11 features. C++ 14 is still a ways out, but we're finally starting to use some of the C++ 11 features. We were able to use these. And I remembered, Herb and Scott had told me all about these. And I didn't remember a thing about how to use them. So I had to relearn how to use them, and I thought I'd share with you what I learned. So in case you want to use them and your group is allowing you to use them now, they'll be fresh in your mind. So that in mind, let's get started. Let me just check and make sure I'm on the right side. Yes. OK. So C++ 11 is a whole new language. There's a lot of things that have changed with the language. So these are some links that I have. And all the slides will be put up on our website afterwards. I've already mailed them to Lloyd, so I can't possibly forget that part. They talk about what's new in C++. So this is a link to the copy elision itself, although I'm going to cover most of the things in that link. This link here talks about just some of the more interesting C++ 11 features. Let's see, this link here talks about what, C++ 11 features every developer should know, and some of the biggest changes in C++ 11. So I'm not going to cover all of them tonight. And if you really like tonight's talk, maybe you can twist my arm and ask Lloyd to let me come up here again and talk about some more of them, and I'll study and do some more. All right, so why should we care about move constructors? OK, so you can construct something by moving it. Big deal. Well, we usually meet in building 40, and I was going to point over to building 40. But we're in building 37 tonight. But in building 40, during the Windows XP Service Pack 1 days, the Windows networking team came up with a whole new TCP/IP stack, all the way down from the NDIS driver at the bottom, right above the hardware, through the different layers of the kernel, including all the I/O packets that were flying around the Windows NT kernel. That was awesome. It was much faster than everything that had been made before. It was much more robust than anything that had been made before. So Dave Thaler, who worked over in Building 40 at the time, was the architect behind it. And the big thing he did to improve it more than anything else was he arranged for the data to only be copied once. So from the time it comes in from the network, it would get copied exactly once as it went all the way up the stack to the final place where it was given to the user. And that ended up being a huge perf win. So in some of your code, you may also find some really big perf wins by making sure the data gets copied only once. Yes?
I just want to make sure I understand your definition. It's in some input buffer off of the hardware, the network hardware, and the one copy is into user space where the user wants it.
Yes,
correct?
Or into memory that will eventually be given to the user.
Yeah, OK, fine.
Yep. OK, any more questions? All right, so What I've just described is perfect forwarding. You take something from one layer and just keep passing it around without having to copy it so it gets to exactly where it needs to be. So the way perfect forwarding works is you can construct return variables, return values in temporary variables that are actually the place that's being returned. So there's no temporary copy that has to be made. And there's no copying to the return value because it's already built in the place it's going to be equal to. So if you imagine variable equals function call, the function call returns something. Instead of making it temporary, they just write it straight into the variable from the function call itself. This optimization is done by the C++ compiler behind the scenes, but that's what makes perfect forwarding work properly for us. So as I say here, C++ does all this for you under the hood, under the name of copy elision. And you can follow that first link on the first slide to get all the proper C++ talk about it. So one of the things we're going to need to talk about to explain this properly is the difference between an L value and an R value. Now, when I first started doing C++ and I would read the specs and the standards, I thought, OK, L value, that's the stuff on the left-hand side of the equal sign. Then you have an equal sign. Then R value, that's stuff on the right-hand part of the equal sign. Well, that's good, but it doesn't quite go far enough. The important part about L values for the purpose of the move constructor, the important part about R values is that R values have no name. And the fact that they don't have a name is an important thing which allows them to be moved around. If they had a name, you couldn't do that. So an L value has a name and allocated storage. An R value is a temporary which has storage but no name. We're going to see a new syntax, which is the ampersand ampersand. Now, of course, we've all seen ampersand ampersand before. We use it with every logical comparison. But now we're using it to mean something different. So just like the two angle brackets here don't mean outputting something to a stream, the two ampersands don't mean a logical and. They mean an R value reference. So this means it's a reference to one of these R values. So it's a reference to a place in memory. Now, I grew up in a Presbyterian background, and right about now you'd expect the lay minister to say, all rise while we read from the holy C++ standard. OK, you don't have to rise. But this is what the C++ standard has to say about it. When a nameless temporary, not bound to any references, would be moved or copied into an object of the same type, ignoring top-level CV qualifications, the copy or move is omitted. When that temporary is constructed, it's constructed directly in the, directly in the storage where it would otherwise be moved to or copied to. When the nameless temporary is the argument of a return statement, this variant of copy elision is known as RVO, return value optimization. And your compiler supports it. So we have new move constructors and new move assignment operators. So basically the way these work under the hood is you've got a pointer, and what it's going to do is it's going to take the pointer out of the old thing, put the pointer into the new thing, and then zero out the pointer in the old thing so you don't end up with an extra copy. So can everybody see this? This is about as big as I could make it and still fit it on a slide. So we've got a memory block, and we're going to copy it with another memory block, R value reference. This is the other one coming in. Let's say it has data, which we initialize with a null pointer, and a length, which we initialize with 0. So what we're going to, and this is just a debugging statement to show you what's going on. What we're going to do is we're going to copy the data pointer and its length from the source object. So we copy the pointer directly, we copy the length directly, and then we're going to go back to the source object, and we're going to zero it out and set the length to 0. So in this case, the memory block has been not copied, but moved. The old guy doesn't have it anymore. The new guy has it, and off you go. No memory leaks you need to worry about. Likewise, there's a move assignment operator, which works almost exactly the same way, just as assignment operators and copy constructors work almost exactly the same way. So again, notice this here, ampersand ampersand for our R value reference. And what we're going to do is check to make sure that we're not assigning to itself. And then once we know that we're not, we can free the data of the new object. We can copy the data from the old object into the new object, copy the length, and then clear out the old object and return this. And that's all there is. So whenever you're running through the code, you see operators with these double ampersands, you'll know that it's a move operator or a move constructor. So the next thing that surprised me was standard move. So who knows what standard move is? Got a couple? So the thing that surprised me is I thought standard move was this ultimately awesome macro that, or not macro, ultimately awesome function that would somehow take what you had and make sure that it moved. It doesn't actually move anything. In fact, it's really simple. All that it does is it casts the thing you're looking at to an R-value reference. And then the compiler does the move under the hood. So the compiler is once again doing things for you. So standard move looks awesome, but doesn't really do anything but cast, which you could have done yourself, but it makes your code easy to read because it communicates your intention to move something. So one of the things I discovered is you can't use const while moving. So I've mentioned before that I work on a Chrome, and in the Chromium code base, they love const references. Because instead of passing around a big struct, you're just passing around a reference to the struct. Only one pointer value has to be copied. So with const reference, you can pass things around all over. You're not worried about modifying the original thing or destroying the original thing. So they wanted me to pass everything by const reference. But if you try doing that with move pointers, it's not going to work, because if you remember those move constructor, the move assignment operator that we looked at, are going to destroy the old thing. So we can't really call the old thing const because it's actually being destroyed. So now I'm going to talk about some things we do specific to the Chromium code base. It's a shame Bartaj isn't here because he loved this next part. So we have something called base bind, and what it does is it creates a wrapped callback function. So basically it's going to create a functor object that you can add additional arguments to by currying, which is the part that Bartaj would love because Bartaj thinks currying in Haskell is the best thing ever. So the problem we run into is when we try to use base bind demands that we use const in our code base, but we can't use const if we're going to move something because it will modify the data. So in our code base, we had to have a separate solution for it. And our solution was we had another macro base past, which is basically just casting things around and making the syntactic sugar constraints, or making the constraints happy by using a little bit of syntactic sugar. So maybe you won't need to do this in your code base, but it also does the cast for the standard move, so we don't need to use both. So what is the pattern for passing something up? So first I'm going to describe the problem we ran into. So in my code, it runs on the Android phone, and we use a SQLite database, and the database runs on a different thread. So anytime we make a call to the SQLite database, the call needs to be asynchronous. So I've got one level of code, which is the code that's my client, which is calling another level of code which sits above the database, which is calling another level of code which is a database accessor, and then there's a database itself below it. So we'll make a database operation. The database accessor will get the data, and then the database accessor will send a call back to the database manager layer, which will then send another call back to my calling code. So after we make the data, there's 2 or 3 or 4 copies of it as we're sending it around through the chain of callbacks to go back up. So my boss said, "Why are we doing this? We can use C++11 now." I said, "I don't remember how that works." So I got a chance to go figure it out, and that's where this talk came from. So how does it work? So my top level manager code was a request coordinator, and I'll give a URL later if you want to actually look at the change list that added all this in that shows it from the request coordinator's point of view. And see, what we do here is we have a callback, and the thing that we're going to pass around is a vector of unique pointers to requests. So you can't put smart pointers in a container, but you can put unique pointers in a container, and you can make it a vector of them. And that's what we're going to be moving. So when we run the callback, we're going to call standard move on these requests. Now when we're passing something to the callback, this is the incantation we use. Since it's Chrome specific, I don't think you'll get much of me trying to explain it. Do you have a question? Oh, OK. So I promise you a URL. So this is the URL, and it will be in the slides that go out. So if you want to see a change where I applied this pattern to several layers going up, here's an example of how to do it. So basically, I return a vector of smart pointers all the way up the chain using moves at every layer so that no copies ever get made. You could also return a vector of items the same way. It doesn't matter if it's smart pointers or items, anything you want to move. So what are some gotchas? When I tried doing this, I ran into all sorts of horrible compile errors. Now, compile errors are no new thing. We're used to them. They happen. But those templated compile errors, you get maybe about this much output, and somewhere in there is a hint about what the actual error might be. So these are some solutions that I use for finding out where the error might be. So the first problem I had is I might have left a reference somewhere. Since I was converting something that used a bunch of references that we're copying, leaving a single reference somewhere will cause a problem. I might have marked something const. When I was making template errors, one of the things I found out that they're very hard to read. So generally, I would just look for, OK, what's the line of my code that's somewhere in this long 2-page error stack? OK, it says my file requestcoordinator.cc had an error at line 57. Ignore the rest of it except for the line number. Go to my file, look at that, and check the types. And usually, a type was off. And this worked for about 90 to 93% of the errors that I got. So template errors are very hard to read. Inspect your code carefully. Make sure that all the types are what you think they should be. And then experiment. So, OK, so maybe I needed a R-value reference instead of a reference. So try making something into an R-value reference. Try making something into L-value. Try taking off const. Try adding const. And sooner or later, you will likely get to the right place. Now, I'll go further. I have a couple specific strategies. So on the next page, I'm going to show you some actual template errors with all the irrelevant stuff taken out. So how to read these? The actual error is usually at the top. I believe this was done with a Clang compiler. Normally, a type somewhere doesn't match. Or maybe base bind had some requirement that I didn't fulfill properly. Look for the first line of my code. Double check all the types in that line. Make sure I use standard move or base passed. And look for the word to. I'll show you what I mean by looking for the word to. So here's a sample compile error. I'm sorry it's small to read. As you can see, I've removed huge gaps in the middle of it. So this is originally about 2 pages worth. I've copied just the relevant lines. So error, call to deleted constructor of this long type. Type mistakenly declared const. So if you declare your type const, of course, you're not going to be able to construct that type because it's been constructed somewhere else. You've just got a const reference to it. And if you accidentally don't refer to it as a reference, then it will think you're trying to build it. And the error you get is call to deleted constructor, which wasn't very obvious to me. So once again, I really should read this type mismatch. And what I really should do is look for the line of my code, go to that line number, and check out the types and find the type mismatch. Another sample compile error. So this time, I've highlighted the word to since I said to look for the word to. And what it's trying to do is it's trying to convert an offline pages save page request to a vector standard unique pointer of offline pages save page request. And this other stuff is just the deleter that it's going to use. So once again, what we have is a type mismatch. And this is the first line of my code. And that's the line where I needed to go to find it. In this case, I forgot to call standard move. So it wanted an R-value reference. Because I didn't call standard move, it didn't have one. And it complained of a type mismatch. One more compile error. So once again, we have the word to here, which tells me that it's trying to convert one big, long, hairy type to another big, long, hairy type. As I say, there's about 2 pages of error messages in between. And then this is the first one of my files that's on the list. Line 308, request queue store SQL. Another page of error messages here. And the problem was, in this case, I forgot the base passed macro that I mentioned earlier that was required to be used with base bind. And that's the presentation. So I apologize it's a little bit short, but it leaves us more time for questions. And hopefully you won't mind a little bit getting too much. You won't mind too much getting a little bit of time back. So, are there any questions?
Have you ever dealt with universal references?
I have not. Anything else? Yes? Nope, I didn't measure the performance. So this is a part of the system that doesn't get called very often. And my boss objected to the performance in this case on moral grounds, that we could do better, more so than it was causing any serious performance problems. Now in the TCP/IP stack, it made a huge difference. Now of course this was actually written in about '06, so the CPP 11 didn't exist yet. And they used it all in C and C++ directly by making only one copy, by being very careful. But nowadays it's a lot easier to do with the move constructor and the move assignment operator. Yes?
On your slide where you first introduced STD move and said, really it's just a cast and the compiler does the work. That, I guess, is, can you explain that a little bit as far as what standard move has an argument?
So when the compiler sees an R-value reference and it's moving that R-value reference across an equal sign, the compiler knows that it can just construct it, the thing the R-value reference is being built, over on the other side of the equal sign. So by casting it to an R-value reference, the compiler then knew that it could apply the return value optimization that we talked about earlier and build it over on the other side of the equal sign, and that's what happens. Does that answer your question? Sure.
So then, so that implies that the type you're dealing with, you have defined the move constructor or move assignment?
Yes. Well, sort of. So if the type you're constructing is an int, the compiler's done that for you. So if I'm just assigning something to an int variable and there's a long calculation that makes an int, it'll make that long calculation and store the answer in the variable without doing a copy.
So if I create an item of my class with a regular constructor and then have a const reference variable to it, then I want to, somewhere in the middle of the function, move it to another variable space, then I can, that's what I use that move, SD move for?
So if
you can't do anything because the move is trying to destroy the original thing as it moves something over.
Okay, so if I just took the const part off that reference.
Right, so if you had a reference, then you might be able to move it over.
And so, like, after that assignment of new variable equals SD move of my reference, the next line I expect the data inside to have been sort of moved to the other variable.
Right, at that point, the data inside should have moved to the other variable. The original variable should have been cleared.
Yeah.
Okay, any more questions? Yes?
It's sort of a sharing an old trick on it wrote years ago. Very often the compiler presents you with incomprehensible error messages as you were saying. And one thing that I used to do is, if I know that ultimately it is a type conversion error, but I don't know which type is at fault, or which expression or which sub-expression is at fault, what I do is I say something like int x equals, and then I copy that expression in the new statement. And then the next error that I get from the compiler would be cannot convert from type var to int. And type y is what I actually need to know. That I've used it for many years, and it's always been useful tool for deciphering errors like that.
That sounds like an awesome shortcut. Thanks for sharing. Lloyd.
Yeah, so as I remember with this, I forget all the details, there was a half a dozen instances where you can construct this and it doesn't actually move. The optimization doesn't actually occur. Did you find any good ways for actually going in and testing? So, like, I'm writing a bunch of code and I want to make sure I'm actually moving and the compiler's just not, ignoring and jumping out of the optimization. Did you find a good way to detect that or instrument that other than just, perf measurements?
It wasn't something that I did during this particular experiment while I was moving the code. What we normally do in my work is we write unit tests for everything, and we would write a unit test to catch that.
Okay.
And then if that doesn't happen, we know that there's something wrong with the compiler. Now, when I said your compiler supports it, I was making assumptions that you were programming for some desktop platform or something like Android or iOS. If you're programming for some of the Internet of Things devices that are using very old compilers, it might be they don't support that properly yet.
So if I could try to understand this correctly, because I didn't see an example of actually you using it. I have a structure, and I have declared, structure variable foo equals some function. It doesn't actually inside the function. There's an int from the structure that I'm assigning to. It assigns it to some internal temporary or whatever. But what happens is at the return, it plays around with the pointers and moves.
So now that's return. So while it's calculating an expression, it has to put that expression somewhere. Instead of putting that expression into a temporary storage and then copying it into the final storage, then using the return value optimization will copy directly into the final storage. Now your question is slightly different.
My question is different. It's how does it get the foo, which is at memory location 1000, into a function that is going to refer to it? And I don't think it's doing that unless I'm understanding it wrong. This is where I'm hoping it's doing. What it's doing is you've got a pointer to a data area as your structure that foo is, and you're storing the results into that data area that's actually part of your function, and then you're moving foo to point to that data area. Is that correct?
So it sort of depends on what foo is. So once Scott Myers gave a talk here, what does f of x mean? And f of x can mean 7 different things. It might be a macro invocation, it might be a function, it might be a template instantiation, it might be a specialized template instantiation, and the list went on. So let's say that foo is a class. And let's say you're doing foo equals some computation. And the computation is going to create a foo object that's going to return foo. So inside the computation, it's going to assign to the x variable of foo.
So it's actually manipulating that data object, that class.
Right. Now foo is declared, let's say in this case foo is declared on the stack somewhere. So it knows where foo is on the stack. And if you're assigning
During
foo.x,
the execution of the function that's building it?
I believe
How does it get that name, which is on the right-hand side of the equal sign, into the function, is what I'm asking.
Right. And the answer is compiler magic, deep compiler magic. Now, that sounds like I'm waving my hands, right?
Yeah.
But let's go one step deeper. So I'm not a compiler guy, and Walter's not here tonight, so I'm not able to ask him. But I would imagine to make this kind of an optimization work, it requires a lot of very careful bookkeeping about what you're doing.
And is it also...
So while you're compiling the function knows that it returns a foo, right? So the code that is going to insert the call to the function knows that this thing returns a foo, and all it needs to know is where to put the foo.
So in
So
effect,
if the
an
compiler
extra...
magic can pass in where to put the foo to the function's actual call, even though it's not an argument that you put on the stack.
It's adding an invisible argument to the function.
Effectively, yes. Although
Like
it is putting
this
it
or something like that.
Yes, I understand that it's akin to this, but that's in effect what it's doing. It's adding an extra argument to the function. That to me is makes total sense answer, right? Which in effect has nothing to do with move other than that it's hiding it. That's what's going on.
Something like that. So for instance, it might not be using an extra parameter on the stack. It might be using a register. It might be
Same difference.
encoding some value in there. I'll get to you next. I think you had his hand up first. Yes?
Do you know any situation where pursuing this sort of optimization would be counterproductive? Or
There's always times when optimizations are counterproductive. I don't have any specific counterexamples for
Okay.
this one. I'll get to you next. I promised it first.
Go ahead and add your hit code.
Okay.
Well, I remember what it was I was doing.
What's your question?
Well, it sounds like from what you're talking about, there's a difference between return value optimization and the move stuff.
Yeah.
Like the move stuff is code that you write, and then you try to get the compiler to execute it because you know that I prefer a move than a copy.
Yes.
right? And so I think like from one of the examples that you had was your like memory block or something, to where, you know, if I have memory block and I want to assign the result of the function which returns the memory block, and somehow it creates it and just makes that assignment. Like at that point, I guess one question is, how do you know what's happening right there, whether that would become a move assignment or that would be a return value optimization style thing?
Yep, that's a good question. I don't know the answer, sorry. I've delved into this deep enough to solve my problem, but not as deep as to present a large paper on it.
Well, if you do, so I guess maybe as another style question would be, if you're writing a function, right, the double ampersand syntax isn't a part of your like return value.
Mm-hmm.
Is that correct?
I don't think I understand your question.
It's not like I return I don't know what to call it, the double ampersand.
So double ampersand is an R value reference.
Yeah, so, but when I write a function, I don't make a claim that I'm returning that.
You don't return R value references,
Yeah,
I think.
right. So I just return either the class instance or a reference, a non-const reference to that. And the only spot that I really use that double ampersand is inside the declaration of my move constructor and move assignment.
Generally speaking, yes, but you also use it implicitly when you're calling standard move.
Yeah, right.
So let's see, I think your question was next, and are you ready with yours?
Yeah, I'm ready.
Okay, so let me take Kim's and use it for you, then I'll come to you, and then it's your turn.
Okay. I think it's important to realize that the return value optimization happened before C++ 11. What came with C++ 11 is a way to be explicit about it with the double ampersand and the move constructors. Return value optimization does not require move constructors. It's a whole different thing. And the return value optimization is in fact compiler magic. Move constructors is explicit, driven by the program.
Yeah,
I think that's very good. Thanks.
I was going to add as well that, yeah, you know, be careful about mingling the two together. Another way I think about it, yeah, another way I think about it is when you have syntax where normally a copy would be performed, but for some reason you do not want a copy, but you explicitly want to move, that's where standard move is used. Return value optimization, all that is allows the compiler to elide or remove a copy that may or may not be needed because it knows where that object is going to end up. But if you're doing A equals B, and you want to move B to A, normally if you copy, you say standard move. Of course, the side effect is that B is going to be no longer up, or it's going to be empty.
Yeah.
And there are times you want to copy, or there are times you want to move something instead of copying something.
Yeah, that makes sense.
Okay, thanks. I think it's his turn next. I'll get to you after him.
there were a couple of questions about how do you know that copying doesn't actually happen. So number one, of course, you can do unit testing and performance testing, but copying is fast. It's hard to detect. So number one is make copy constructor of your class, delete the function, or make it private. And then it will never be invoked because it says the C++ compiler will ensure that it doesn't get invoked. If that is not possible or practical, breakpoint there, put a printf, run your program, and make sure that you don't keep that code. That's a very reliable way of making sure that copying doesn't happen.
Yep, that's absolutely right.
Can you?
I wish I had said it first.
I didn't hear all of what you said.
So the question was, how do you make sure that copying doesn't happen, right? And there are two ways. One is making your copy constructor private or deleted.
Yeah.
In which case, it by definition will never happen. Or if that's not possible, put a breakpoint or a printf in your copy constructor. Run your program on the debugger and make sure that you never hit that breakpoint. Does that make sense? Because every time you copy, a copy constructor, the copy constructor gets invoked for the object that you're copying.
If the argument is a left-hand value. If it's a right-hand value and a move constructor exists, then the move constructor exists.
Which is what you want, right?
presumably.
Yes. So Lloyd, does that answer your question earlier?
Yes, it does. Thank you very much.
Okay, I think you were next. Oh, wasn't you? In that case, it's your turn.
One thing that helped me understand the move constructors, or the move semantics, is it's not always necessarily an optimization to like speed things up. For example, like a unique pointer.
Right, there are times when you only want one of something.
Right. So you can't copy a unique pointer because there should only be one. So being able to move it allows that to be possible.
Okay, think you have the next one?
Yeah, similar just comment is that, it seems like your class definition needs this cooperative memory or something that can be moved as a single operation, but really you're effectively moving a chunk of things. So you just have a class with a bunch of primitives, primitive values, then move is effectively a copy depending on what you do to the other side after the...
Yeah, depending on how you structure your data, you don't need to use this at all. Anything else? All right, well, I think we're done. Thank you, everybody, for listening.